Today, we're going to look at one of the most elegant ideas in all of computer science. We're going to pull back the curtain on that hidden process that lets a computer go from just reading our code to actually understanding what we want it to do. I mean, it seems so simple, right? Almost trivial. But behind this basic bit of math is this really beautiful, systematic process that turns abstract symbols into real, concrete actions. And, well, that's the journey we're going to go on together. Okay, so first things first. We have to start with a really fundamental truth. Before a computer can do anything smart with our code, it just sees a long string of characters. That's it. Yep, that's right. That line of code, 3 plus 4, isn't 3 plus 4 to the machine. Not at first. It's just the character 3, then a space, a plus symbol, another space, and the character 4. It's pure, unstructured text. Kind of like a pile of raw materials waiting to be shaped. So how do we give that raw material some shape? Well, just like in construction, you can't just start building. You need a plan. You need a blueprint. And in the world of programming, that blueprint is called a grammar. It's basically the set of rules that tells the computer how all those individual characters are allowed to fit together. It's the architectural plan for the entire language. Now, in computer science, this blueprint has a bit of a formal name, a context-free grammar. But don't let that intimidate you. It's really just a list of rules that defines what a valid sentence, or a valid line of code, looks like. And at this stage, it doesn't care about meaning at all. Its only job is to check if the structure is correct. And this is what you get. This shows it perfectly. Once the computer uses those grammar rules on our text, it can build this thing, a parse tree. This is the structural frame of our code. See how the plus is at the top, connecting the 3 and the 4? The structure is suddenly crystal clear. But, a frame isn't a finished house. We've got the structure, but we still don't have the meaning. So our next step is to figure out, well, how do we add the instructions that actually bring this structure to life? And this is the million-dollar question, isn't it? The parse tree shows us how the 3, the plus, and the 4 all fit together, but it doesn't actually tell the computer to, add them. So how do we bridge that gap? Well, the answer lies in separating two key ideas. We have syntax, which is the structure. That's the steel frame of this building. And then we have semantics, which is the meaning. That's the stuff that makes the building useful, like the electrical wiring and the plumbing. And this is our big idea for today, a syntax-directed definition, or SDD for short. It's what formally connects those two worlds. It takes our grammar, our blueprint, and for each and every rule, it attaches a specific semantic action, which is just a fancy way of saying an instruction. It's the instruction manual that comes with the blueprint. So let's see how this actually works. For the grammar rule that recognizes a pattern like number plus number, the SDD attaches a super simple action, perform addition. So when the computer sees that structure in the code, it looks up the matching rule in its blueprint, and then it just executes the action that's attached. The structure directly tells it what to do. Now, what's so cool is that this idea of attaching actions to rules goes way beyond simple math. We can attach more than just instructions to do something. We can also attach little bits of information to our structure. And that's how compilers understand more complex ideas, like data types. For instance, we can attach these extra pieces of information called attributes to the different spots on our parse tree. Just think of them like little sticky notes. So here, the notes are telling us that index is an integer and A is an array of integers. This information gets carried along for the ride as the tree gets processed. And these attributes aren't just random. The rules in the syntax-directed definition are what tell the compiler how to write and check these little notes. This is exactly how a compiler catches errors, like if you accidentally try to add a number to a piece of text. It's a whole system that makes sure the program isn't just structurally correct, but that it's also semantically, logical. So, when we take a step back and look at the whole picture, what have we really learned? We've basically found a whole new way to see how code actually works. It's this wonderfully clean progression. We start with just a bunch of simple characters, we use a grammar to build a structure out of them, and then we use a syntax-directed definition to walk over that structure and figure out its meaning. It's an incredibly orderly and reliable process, and honestly, that reliability is what makes modern programming languages so powerful. This quote from the source material just nails it. The meaning isn't some separate, mysterious thing. It flows directly from the code's grammatical shape. In other words, the structure defines the meaning. So, if you take just one thing away from all this, I really hope it's this. Code isn't magic. It's not. It's a system. A system of simple, clear rules that when you combine them can build systems of incredible complexity and, well, beauty.
At the end of the day, it's a lot like that, isn't it? A few simple architectural rules, like how a wall meets a floor or how a window fits inside a wall, can be combined over and over to create something as complex and as varied as a sprawling city. That same elegant principle applies to the code that powers our entire world.